We all know that when you drop something, it falls straight down, right? I mean, that's just basic gravity. But what if I told you that here, on our spinning planet, straight down isn't really straight at all? Today, we're going to dig into a really cool physics problem that reveals a hidden push that's acting on everything that moves.
So let's set up the problem. Picture this. You are standing at the equator, way up on a tower that's 500 meters high. You take a rock, and you drop it. Simple enough? The question is, where does it hit the ground? Go on, take a guess.
Your first thought, your intuition, is probably that it's going to land right at the base of the tower. I mean, that just makes sense, right? Gravity pulls things straight down. But that's where things get interesting. That answer is wrong.
Yeah, not quite. The reason our intuition leads us astray is because we're forgetting a massive piece of the puzzle. We live on a gigantic spinning ball. In physics terms, we're in what's called a non-inertial reference frame. And trying to describe motion from a platform that's constantly moving, well, that changes everything. Okay, so here's our game plan for today. We're going to start by picking apart that intuitive straight fall idea. Then we'll get into the nitty-gritty of the Earth's rotation. We'll meet the force that's causing all the mischief, actually run the numbers to get an answer, and finally, look at the big picture. Let's dive in.
So, first up, this idea of a straight fall. Look, in a lot of introductory physics problems, we simplify things. We just pretend the Earth is sitting still because, honestly, it makes the math way easier. But for this problem, that's the one thing we absolutely can't ignore.
To really get this, you have to think about two different points of view. Imagine you're an astronaut floating in space, just watching the Earth. For you, in an inertial frame, Newton's laws are perfect. An object in motion stays in motion, in a straight line. Simple. But for us down here, on the spinning merry-go-round, that same straight path looks like a curve. And to make sense of that apparent curve, we actually have to invent some forces.
And this is really the heart of it, because we live on the spinning frame of reference. Straight lines don't always look so straight from our perspective.
Now, these invented forces are called fictitious forces, but don't let that name fool you, because their effects are 100% real. They're not a physical push or a pull like gravity or magnetism. Instead, they're just a consequence of us doing physics from a moving viewpoint. You've felt one of these before, the centrifugal force that seems to push you outwards on a merry-go-round. The other famous one is the one we care about today, the Coriolis force.
So let's properly introduce the star of our show, the reason our falling rock doesn't land where we expect it to. This is the Coriolis force, the hidden push of our planet's rotation.
Okay, here's the formula, but stick with me. It's not as scary as it looks. All it's really saying is that this force depends on the mass of the object, its velocity, and omega. That's just how fast the Earth is spinning. The really important part is that little x. It's a cross product, which is just a mathematical way of saying this force is always a sideways push, totally perpendicular to the way the object is already moving.
So what does this force actually do? Well, a couple of key things. First, it only works on things that are already moving. If you're standing still relative to the Earth, nothing happens. But the second you start moving, this force gives you a little nudge sideways. This leads to a really famous rule. In the northern hemisphere, it pushes moving things to the right, and in the southern hemisphere, it pushes them to the left.
All right, enough with the theory. Let's roll up our sleeves and actually use this to solve our 500-meter tower problem. We're going to break it down step by step so it's super clear.
First things first, we need to know how long our rock is even in the air. This is the easiest part of the whole problem. You've probably done it 100 times. We just use a basic freefall equation.
You know this one. Height equals 1/2 gt squared. We just rearrange it to solve for time. When you plug in 500 meters for the height, you get a fall time of just over 10 seconds. So that's our window. The Coriolis force has about 10 seconds to do its work. Now for the part that can trip people up. Which direction is the push? Remember, we're at the equator, so the Earth's rotation vector, omega, points straight north along the axis. The rock's velocity is straight down. If you use what's called the right-hand rule, point the fingers of your right hand down, then curl them towards the north, your thumb points east. That's our direction. The push is to the east.
So we have a force, and we have the time it acts for. Now we can figure out the distance. That eastward force gives the rock a constant eastward acceleration. From that, we can figure out how much sideways speed it picks up. And if we just add up all that sideways motion over the full 10 seconds of falling, we'll get the final distance it was pushed.
After you do all that math, you land on this really nice expression right here. The total sideways deviation depends on Earth's rotation, the height, and gravity. So now all we have to do is plug in the numbers.
Okay, we've done the math. Let's see what the final answer is. And then I want to show you a much more intuitive, kind of cooler way to understand why it has to be eastward, without any of the complicated formulas.
And here it is. The rock lands 24 centimeters to the east of where it started. It's not a huge distance, for sure, but it's undeniable. It did not fall straight down.
So why east? Forget the right-hand rule for a second, and just think about this. This is the simple, physical reason, and it's brilliant. Here's the way to think about it. The top of that 500-meter tower is just a little bit farther from the center of the Earth than the base is, and since the whole Earth rotates together in 24 hours, that means the top of the tower is actually moving eastward a tiny bit faster than the ground. So when you drop the rock, it has that extra eastward speed. As it falls down, the ground beneath it is moving a little slower, it can't quite keep up, so the rock naturally lands just a little bit ahead of the base, to the east. Cool, right?
So we've solved it, but before we finish up, I want to talk about the common mistakes I see students make on problems like this, and then connect this tiny effect to some massive, real-world stuff.
Okay, if you ever have to solve a problem like this, here are the traps to avoid. The biggest one, honestly, is just forgetting the Earth rotates at all and saying it falls straight down. The second is getting the right-hand rule backwards and saying it deviates west instead of east. And please, whatever you do, don't let the word fictitious make you think this force isn't real. Its effects are very, very real.
Think about it. We just saw this force cause a tiny 24-centimeter shift on a rock falling for only 10 seconds. Now, imagine that same force acting on a gigantic mass of air that's moving for days across thousands of kilometers. Well, that's exactly what gives hurricanes and cyclones their spin. It's this tiny, hidden push, scaled up, that literally shapes the weather on our entire planet.